Modular self-reconfiguring robotic systems or self-reconfigurable modular robots are autonomous kinematic machines with variable morphology. Beyond conventional actuation, sensing and control typically found in fixed-morphology robots. Self-reconfiguring robots are also able to deliberately change their own shape by rearranging the connectivity of their parts, in order to adapt to new circumstances, perform new tasks, or recover from damage. For example, a robot made of such components could assume a worm-like shape to move through a narrow pipe, reassemble into something with spider-like legs to cross uneven terrain, then form a third arbitrary object to move quickly over a fairly flat terrain. It can also be used for making fixed objects, such as walls, shelters, or buildings. In some cases this involves each module having two or more connectors for connecting several together. They can contain electronics, sensors, computer processors, memory, and power supplies. They can also contain actuators that are used for manipulating their location in the environment and in relation with each other. A feature found in some cases is the ability of the modules to automatically connect and disconnect themselves to and from each other, and to form into many objects or perform many tasks moving or manipulating the environment. By saying self-reconfiguring or self-reconfigurable, it means that the mechanism or device is capable of utilizing its own system of control, such as with actuators or stochastic means, to change its overall structural shape, having the quality of being modular. In self-reconfiguring modular robotics is to say that the same module or set of modules can be added to or removed from the system, as opposed to being generically modularized in the broader sense. The underlying intent is to have an indefinite number of identical modules, or a finite and relatively small set of identical modules, in a mesh or matrix structure of self-reconfigurable modules. Self-reconfiguration is also different from the concept of self-replication, and self-replication is not necessarily a quality that a self-reconfigurable module or collection of such modules can or must possess. A matrix of n number of modules does not need to be able to increase the quantity of modules to greater than n to be considered self-reconfigurable. It is sufficient for self-reconfigurable modules to be a device that is produced at a conventional factory, where dedicated machines stamp or mold components, and factory workers on an assembly line assemble the components to build each module. There are two basic types of methods of segment articulation that self-reconfigurable mechanisms can utilize to reshape their structures: chain reconfiguration and lattice reconfiguration. Structure and control. Modular robots are usually composed of multiple building blocks of a relatively small repertoire, with uniform docking interfaces that allow transfer of mechanical forces and moments, electrical power and communication throughout the robot. The modular building blocks usually consist of some primary structural actuated unit, and potentially additional specialized units such as grippers, feet, wheels, cameras, payload and energy storage and generation. A taxonomy of architectures. Modular self-reconfiguring robotic systems can be generally classified into several architectural groups by the geometric arrangement of their unit. Several systems exhibit hybrid properties, and modular robots have also been classified into the two categories of mobile configuration change and whole-body locomotion. Lattice architecture have their units connecting their docking interfaces at points into virtual cells of some regular grid. This network of docking points can be compared to atoms in a crystal and the grid to the lattice of that crystal. Therefore, the kinematical features of lattice robots can be characterized by their corresponding crystallographic displacement groups. Usually few units are sufficient to accomplish a reconfiguration step. Lattice architectures allows a simpler mechanical design and a simpler computational representation and reconfiguration planning that can be more easily scaled to complex systems. Chain architecture do not use a virtual network of docking points for their units. The units are able to reach any point in the space and are therefore more versatile. But a chain of many units may be necessary to reach a point, making it usually more difficult to accomplish a reconfiguration step. Such systems are also more computationally difficult to represent and analyze. Hybrid architecture takes advantages of both previous architectures. Control and mechanism are designed for lattice reconfiguration but also allow to reach any point in the space. Modular robotic systems can also be classified according to the way by which units are reconfigured into place. Deterministic reconfiguration relies on units moving or being directly manipulated into their target location during reconfiguration. The exact location of each unit is known at all times. Reconfiguration times can be guaranteed, but sophisticated feedback control is necessary to assure precise manipulation. Macro-scale systems are usually deterministic. Stochastic reconfiguration relies on units moving around using statistical processes. The exact location of each unit only known when it is connected to the main structure, but it may take unknown paths to move between locations. Reconfiguration times can be guaranteed only statistically. Stochastic architectures are more favorable at micro scales. Modular robotic systems are also generally classified depending on the design of the modules. Homogeneous modular robot systems have many modules of the same design forming a structure suitable to perform the required task. An advantage over other systems is that they are simple to scale in size by adding more units. A commonly described disadvantage is limits to functionality. These systems often require more modules to achieve a given function than heterogeneous systems. Heterogeneous modular robot systems have different modules, each of which do specialized functions, forming a structure suitable to perform a task. An advantage is compactness, and the versatility to design and add units to perform any task. A commonly described disadvantage is an increasing complexity of design, manufacturing, and simulation methods. Other modular robotic systems exist which are not self-reconfigurable, and thus do not formally belong to this family of robots, though they may have similar appearance. For example, self-assembling systems may be composed of multiple modules but cannot dynamically control their target shape. Similarly, tensegrity robotics may be composed of multiple interchangeable modules but cannot self-reconfigure. Motivation and inspiration. There are two key motivations for designing modular self-reconfiguring robotic systems. Functional advantage. Self-reconfiguring robotic systems are potentially more robust and more adaptive than conventional systems. The reconfiguration ability allows a robot or a group of robots to disassemble and reassemble machines to form new morphologies that are better suitable for new tasks, such as changing from a legged robot to a snake robot and then to a rolling robot. Since robot parts are interchangeable, machines can also replace faulty parts autonomously, leading to self-repair. Economic advantage. Self-reconfiguring robotic systems can potentially lower overall robot cost by making a range of complex machines out of a single type of mass-produced modules. Both these advantages have not yet been fully realized. A modular robot is likely to be inferior in performance to any single custom robot tailored for a specific task. However, the advantage of modular robotics is only apparent when considering multiple tasks that would normally require a set of different robots. The added degrees of freedom make modular robots more versatile in their potential capabilities, but also incur a performance trade-off and increased mechanical and computational complexities. The quest for self-reconfiguring robotic structures is to some extent inspired by envisioned applications such as long-term space missions that require long-term self-sustaining robotic ecology that can handle unforeseen situations and may require self-repair. This architecture underlies biological systems' ability to physically adapt, grow, heal, and even self-replicate, capabilities that would be desirable in many engineered systems. Application areas. Given these advantages, where would a modular self-reconfigurable system be used? While the system has the promise of being capable of doing a wide variety of things, finding the killer application has been somewhat elusive. Here are several examples. Space exploration. One application that highlights the advantages of self-reconfigurable systems is long-term space missions. These require long-term self-sustaining robotic ecology that can handle unforeseen situations and may require self-repair. Self-reconfigurable systems have the ability to handle tasks that are not known a priori, especially compared to fixed configuration systems. In addition, space missions are highly volume and mass constrained. Sending a robot system that can reconfigure to achieve many tasks may be more effective than sending many robots that each can do one task. Tele Pario. Another example of an application has been coined, Tele Pario, by CMU professors Todd Mowry and Seth Goldstein. Watch the researchers propose to make a moving, physical, three-dimensional replicas of people or objects, so lifelike that human senses would accept them as real. This would eliminate the need for cumbersome virtual reality gear and overcome the viewing angle limitations of modern 3D approaches. The replicas would mimic the shape and appearance of a person or object being imaged in real time, and as the originals moved, so would their replicas. One aspect of this application is that the main development thrust is geometric representation rather than applying forces to the environment as in a typical robotic manipulation task. This project is widely known as Claytronics or programmable matter. Bucket of stuff. A third long-term vision for these systems has been called bucket of stuff. In this vision, consumers of the future have a container of self-reconfigurable modules, say in their garage, basement, or attic. When the need arises, the consumer calls forth the robots to achieve a task such as clean the gutters or change the oil in the car, and the robot assumes the shape needed and does the task.